In this tutorial, I'll present the fundamentals of how to use forces and sensors in the Kinematik-Software ASOM version 7 to make a kinetostatic analysis. For this purpose, I'll first create an arbitrary simple multibar system, actually a 4-bar system. I'll set the fixed bearings, add a drive to the system to get an animation. I'd better name the significant joints. In this case, I'll just call them A1 and B1. And then I'll give the coupler a more realistic shape with a mass. This must now be connected to the coupler. This is not yet the case. So right mouse click on the object, connect, and then simply select the designated element, the coupler. Now the connection has been made. Then I'll add a mass to the object. Here as well, I first have to select the object to which I want to add the mass, then I can place it the center of mass. Last, I enter a value for the mass, simplified to 1000 kilograms. And I should also name the object mass 1, like this. And I'll set to make this a little more complex, and because it is often needed in practical projects, another force. I'll apply this one also to the coupler, and I want its vector to move along with the coupler, not like this. For this, I'll set the vector mode via right-click to local. This means that the force, there, you can see it now, always has the same relative angle to the coupler, so to say. But it is different from a mass, which can only act vertically downwards in any case. Okay, I'll just name the new force, and then I'll have to make one more modification. I want to have a force value of 1000 Newton, and that without any change, so the characteristics should be flat, parallel to the x-axis. It's not as if we would want to simulate some kind of spring here, but a constant force instead. Like this. What I'm interested in now, in this case, is the necessary torque, or more specifically holding torque, which is needed to hold the system in balance, in kinetostatic balance, if the holding torque is applied right here. And at the same time, perhaps I'd like to know the necessary holding torque if applied to joint B1. So I'll go to the feature Relative Holding Torque and place a sensor, a holding torque sensor, here at both joints A1 and B1. One important note, these sensors do not interfere with each other by default, but each sensor acts as if it were the only sensor in the system, though if you need different behavior, that is possible too. You'd have to choose that deliberately, though, under consideration of corresponding degrees of freedom. In this case, without any further modifications, each sensor acts as though it were alone in the system. Now I'll make a diagram by going on holding torque via right-click on the sensor. I'll name the window holding torques, since we want to view both sensors together. The rest I can leave as it is. That's one sensor down. Notes I can close for now. And now I'll add to this diagram, let's keep the legend, and I'll adapt the name a little bit. holding torque in Newton millimeters at A1. And now I'll add also via right click. By the way, there are other ways to create such diagrams, for example via the corresponding menu ribbon and then selecting the source elements graphically. In general, it's easier to use the context menu though, since then the choices are focused and limited to what is used or needed most often and the source element is already determined. So, second holding torque. Here I'll first select another color, intentionally, and also a diagram window that already exists, holding torques. And it adds the graph to this window. Now we have both holding torques and we can compare them with each other. Maxima, minima, zero crossings, and so on and so on. A quick check. You can see how the values of these holding torques change. And also how they become more alike, just as they should. If I bring the system closer together here, as you can see, the basic shape is similar. And like this, you can see the progression of the torque values and the zero crossings here, whose placement could be easily understood. Well, at least if there wasn't this other force around. But then I can temporarily delete the other force, like this. Now there is only the mass of the coupler object. And in this situation, with no additional forces anywhere in the system, the effective lever length of the mass must obviously be zero to achieve this zero crossing. This has got to be true. The effective lever length has to be zero, since there are no other forces present that could account for such a cancellation. Now, this might not be apparent at first glance, but if you take a look at the position of the instantaneous center of rotation of the coupler at the time of the zero crossing, qualitatively you can see quite clearly. There is just about no lever length left for the action of the mass on the instantaneous center of rotation. After that, the lever gets larger again, and with it the torque value. And here the lever length is zero again, as you can see, again with the instantaneous center of rotation right above where the mass is located, similar to the beginning of the animation. And perhaps a short note as to the instantaneous center of rotation. This is essentially the current center of rotation for an object, in this case the coupler, and in each infinitesimally short moment of time this is indeed the exact point that the coupler rotates about, and with this information it becomes immediately understandable why in this case, with the mass situated directly below such a center of rotation, the torque must be zero, of course. So much for that subject. Additionally, I might, for example, be interested in some bearing loads or in general joint forces. For this, I'll head over to Diagrams and select the feature Joint Forces. Now, I first have to choose the sensor that I want to base my kinetostatic analysis on. This should be readily understandable, since depending on just where I apply my holding torque to balance out my force system, of course I'll get quite different joint forces. So then I say, okay, I'd like to apply my holding torque here, and I want to see the joint force for this joint, and coming from the coupler. Here there are only those two options to choose from, although in this case, with no additional forces acting on the system, it is almost irrelevant whether I choose the coupler or the driver. The forces will be symmetric anyways. So coming from the coupler, and I'll name it joint forces. As x-axis source, I'll leave in the time. On the other hand, maybe I don't want to see just the absolute value, the vector norm, but the individual x and y components. For this, I'll first expand all these sections here. And then I see that here in the y parameters, the vector norm is pre-selected. But I want to show the components additionally, like this. Now I can see the individual components. I'll just move that over there and dock it. The legend I'll close to get more room for the graphs. And here as well, you can of course see the immediate reaction to any changes in joint positions or in the position of the mass. Well, this was now a short introduction to kinetostatic analysis. You can do a lot more than that with this though, with more details and more complex analysis. There will be further tutorials for that. For practice, I would suggest placing different sensors on various kinematic systems like crank slider systems or more complex systems, and to try and determine various kinetostatic values. To make it easier to reproduce the results of this tutorial, the example project presented here will be available as saved project from the download area on our website www.asom.eu. Thank you for watching.